Okay. So welcome everybody. So we are now having Suman Kundu, who will be taking a tutorial for the set of lectures on S matrix by Shiraz Minwalla over the last week. So Suman, over to you.
Thank you. So what I will do, so first I will explain what happened in this 3 lectures. Like in one slide I will try to explain what happened in this 3 lectures by Shiraz. So what is the main motivation for this work was the first conjecture he have mentioned in the lectures, that there are 3 bold conjectures which are not independent, but there are some conjectures, and the last 2 conjectures, second and the third conjecture, will be true if another conjecture is true. That is the name of that conjecture is CRG, or the classical Regev-Growth conjecture. Okay, so this is the more physical condition rather than these conjectures. So what this conjecture says, that all those classical, if you calculate a classical S matrix of an interacting theory, then that Lagrangian will be disallowed if the corresponding S matrix violates, if the corresponding S matrix has a Regev-Growth of greater than S square. Okay, so then that interaction is not there. So that's the CRG conjecture. Now next he gave a proof of this CRG conjecture using bound-on KAWS. So there is a paper by Maldacena and Stanford and Schenker who have bounded a boundary correlator, and that we have shown in our paper that translate to CRG in the bulk. Okay, this he have shown in the second lecture. Now, after getting this proof for any interaction, you will what he did, that he started checking which interaction satisfies the CRG conjecture. So for that, if you want to do a complete if you want to give a complete answer to this question, you have to do a huge full classification of all possible interactions. Okay, 4-point interaction. Now that is done in the previous paper, and Shiraz have explained that the full classification of the S matrix. So you can classify also the possible S matrices coming out of a 2-to-2 scattering. So if here the CRG conjecture is valid for 2-to-2 scattering, and you can classify all possible S matrices, and that is done for scalars, photons, and gravitons with great rigorousness. Okay. And this classification was done in gradation in momenta. So for a fixed number of momenta, how many S matrices are possible, and that's how it was done. Okay. Now after doing this S matrix classification, one can but our motivation was to exclude or include some interaction, or that is Lagrangian terms, right? So there must be some relation between a given Lagrangian and the next matrix. Okay, so the next classification people can do independent of this S matrix classification. You can classify all possible Lagrangians. Okay, so with derivative gradation, and you can easily understand derivative correspond to momenta, because you take derivative on the field and it gives you e to the power IPX gives you a momenta. So it goes actually hand in hand with the gradation of momenta classification. And this gives you a 1-to-1 correspondence between the S matrix and the Lagrangian list. So there is a S matrix classification list, and there is a Lagrangian classification list, and this is graded in derivative, this is graded in momenta, or both of them are 1-to-1 correspondence, and that they have shown. So Shiraz have explained exactly in this order. Okay. Now he have said that these 2 classifications are indeed isomorphic, that is, they are 1-to-1 related. Now, what is the result of this classification? Now you have all the Lagrangians, you have their S matrices, you have a condition that says that if it violates CRG, it will be disallowed. Okay, and the result is this, that for D greater than 6, that is up from 7 or above, Einstein term is the only Lagrangian which satisfies the CRG conjecture at 4-point level. Okay, so this is a very interesting result at classical level. So everything is at classical level. Okay.
You mean D less than 6 or?
D less than 6. I'm extremely sorry. Yes. D greater than 6, there is a extra term comes from the Chi6, and that's an offending term. Previous day there was a discussion on this, that that term might not be there, but it's not excluded by this CRG. Yeah, true. Thank you. Yes.
Equal to 6. Okay. Yeah.
Yes. D less than 7. Yes. Good. So here I will do a very discrete things, like there are very discrete things which Shiraz has left out, that I will complete. So the first thing I will do now, I will do in some order, in the opposite order, but the three things I will do is, one thing is that here in chaos bound. So chaos bound is a calculation of an OTOC. Okay, and CRG is valid for a 2-to-2 scattering, that is a time ordered correlator. Now I will explain how this OTOC, that is out of time ordered correlator, in one theory, one example, that is bound on chaos, becomes a time ordered correlator in CRG in using Rindler coordinate transformation. That is one thing I'll do. And another thing is, so he had explained this part very well, this S matrix classification. I will mostly concentrate on this second part, that is the Lagrangian classification. Okay, using plethystic counting. So that I will explicitly concentrate on, and I will show one good output of this S matrix classification, and that we will see that what it is, like how a Z2 cross Z2 modding gives you there is an identity related to this S matrix classification. I'll say that. Good. So these are the three things that I will classify Lagrangians using plethystic counting. I will enumerate the Baire module, that is the last thing I said, and the time ordering chaos bound so I'll do it in reverse order. Good. So let's start with something totally different, that is supersymmetric quantum mechanics. Okay. So yeah.
Can I ask the question?
Yes.
So when you say that, like there is a mapping between 4-point functions and the things that you get at the level of Lagrangians. So sometimes, like in Lagrangians, you have to include like Chern-Simons terms and so on, gravitational Chern-Simons terms. So do you allow for such things, the things which are not quite gauge invariant, but they're kind of gauge invariant up to boundary terms?
Yes. Boundary is will not affect at all in this calculation, because we are calculating in the bulk 4-point function. So
No, I'm not asking that. I'm asking, when you're talking about Lagrangians, what are, like, do you only allow covariant or invariant scalars in the Lagrangians, or do you allow things which are not diffeom also invariant, also in your Lagrangian?
Which are not diffeomorphism.
Like
I think Chern-Simons will. I see. No. In the photon case, we have not in. I don't think the Chern-Simons is included, because the structure we started with is this derivatives sprinkled, like L derivatives sprinkled on this F mu structure. So these are the basic structures, and to the power 4. So that gives you all possible interactions. So I don't think that Chern-Simons is included, but I should say that parity odd structures are there. So yeah, but parity odd structures with F mu. So I don't think Chern-Simons is there.
Okay.
But I have to check. I should not say I have to check that.
Thank you.
Yeah. Okay, so I will start with some one example where people usually started doing plethystic counting, that is in the supersymmetric theories. So how it is done, I will explain. So in supersymmetric theories, this is the one variable Lagrangian, and this is the corresponding Hamiltonian, where AB dagger is the bosonic creation operator, and AF dagger is fermionic creation operator. And this is the vacuum, which is annihilated by H, Q, and Q bar. These are the supersymmetric operators, and these are the states that you take the vacuum and then act on AB to the power AB dagger to the power n, and that is one bosonic state. Fermionic state is act with one F dagger and then the same AB daggers. Okay. So now how to calculate the partition function? Now partition function is calculated by using very simply, this one comes from the vacuum and then the boson gives you this part and the fermions gives you the same thing because of this same structure. Okay. So if you sum this series, that is 1 plus 2 times this series gives you this. Okay. So this is a very well-known result. Okay. Now we will calculate the same partition function using some different trick. Okay. So the trick is this, that so this trick is exclusive to free theory. Okay. So the spectrum usually is, so for free theory, the spectrum is usually generated by action of all creation operators on the vacuum, and usually the creation operators commute with each other. So the states are the important, and that's how the spectrum is constructed. And the creation operators act independently. Now it is convenient to compute the partition function over single letters. Okay, we will explain what is this single letter mean, and you can calculate a partition function for individual single particles, and this is called a single letter partition function. Okay. And it is used. So we will do this calculation independently for boson and fermion. Here we had to take care of all those things at the same time, looking at the states. But here you can do it letter by letter, that is component by component. If you have a bosonic letter, you will be, so what we are calling it a letter. So the letter is this AB. So a quantity which is acting again and again to construct different states. So here AB dagger is a letter. Okay, here AF dagger is a letter, and so now if you have a single letter, that means so we will denote this single letter partition function by ZB of x and ZF of x. Z is a small z. So the total partition function is ZBX plus ZFX, where you are calculating the ZBX is calculated by a single letter, that is AB dagger, and that represent an x, and for the fermions a single letter represent an x. Okay, so these are the ZB and ZF. Okay, now the next what you will do, that you take this partition function and then sum over all multi-particle states. Okay, now you have a single letter partition function. Now you are constructing a multi-particle partition function, and how it is done, that it is done by this trick, that you have this single letter partition function, and x for bosons, x should be replaced by 1 minus x. Why? Because there are multiple states with this structure, and that gives you 1 minus x. Okay. Now this is the bosonic thing, since multiple AB dagger can act, but for fermions only either there is a AF dagger, or either it is vacuum or AF dagger vacuum. So that's why this is x is replaced by 1 plus x, and that is the fermionic total multi-particle partition function. Now we know that full partition function is multiplication of these two partition functions, and that gives you 1 plus x by 1 minus x. So this is exactly matches with the previous result we have derived. So now this might, yeah.
I have a question about this ZF. You have said that ZF has only two allowed things. One is the vacuum and another is just one fermionic particle.
Yes.
But the vacuum is already included in the bosonic part, right? I mean, bosonic part, ZB.
Yes.
Do we have to again include in the fermionic part as well? I mean,
it's a product, no?
It's a product, yes.
Oh, yes, sir.
Yeah. So it is AB dagger to the power n times AF dagger to the power m. Now m can take only 0 and 1, and n can take 0, 1, 2, 3, and this n gives you this part and m gives you this part. So this is how.
Okay,
yeah. Good. So now ZB, so here a capital ZB correspond to sum over all states obtained by acting with any number of bosonic creation operator, and ZF correspond to the same thing as you said that capital ZF correspond to the states with no fermion and a single fermion. Okay. Now, if theory has multiple types of creation operators, here we had only AB dagger and AF dagger and nothing else. Now we can have multiple. Now, since this has only two things, and we could have easily calculated here. So this calculation was very easy, but it would be complicated if we have multiple components. That is, let's say you have an index here, okay, with this AB dagger. Now that calculation might be complicated, and that's where this plethystic counting becomes very useful. Okay. Now to compute the full partition function, so what we have to do, that we have to take, if we have multiple components like AB dagger, so then we have to calculate single letter partition function for each components and then product over all those components. Okay, so that's how you can calculate the full partition function. Okay, now this particular trick, this x is replaced by 1 by 1 minus x, has a name that is called plethystic exponentiation. Okay, I will explain what is this plethystic exponentiation is. Its notation is PE. Okay, so the definition is this. Okay, the definition is this. So PE acting on fxi, that is a single letter partition function, is exponential of 1 by n f xi to the power n. So x to the power n is inside. Okay. Now you can, so this is the bosonic plethystic exponentiation. This is fermionic plethystic exponentiation. For the fermion, it is tilde and the same thing, but here there are two minus signs. Okay. So this gives you two different kinds of plethystic exponentiation. And as a definition, this capital ZB is just the plethystic exponentiation of this small ZB, that is the single letter partition function, and for ZF this is the same. And now the total Z is this. Okay, we will check that actually if ZB, so previously we said that ZBX is X, right, and ZFX is X because there are only single letters, right? So if you can calculate this, that you can substitute fxi to the power n by x to the power n, and that's what we did. That's what we did here. Okay. Now you can see that this is a log series and the expansion of this function. Okay. Now this gives you 1 by 1 minus x. Exponential of minus log of 1 minus x is 1 by 1 minus x, and this actually gives you the ZB. So previously we did some ad hoc thing that I have just replaced by x by 1 minus x, and that is actually intuitively correct, that it is the bosonic partition function, we know. And ZF, if you calculate P tilde, here there is extra minus sign and the minus 1 to the power n, and that is exactly the series of this log of 1 plus x, and exponential of log of 1 plus x is 1 plus x. So now as a definition, we have that Z is ZB times ZF. Now advantage of this, as I said, the advantage of this trick is you can calculate the single letter partition function for individual components and then just multiply. So that gives you the total partition function. You don't have to think about this works like a direct product. You are just calculating the component by component. Okay. So yeah. So now as I said that this had only two components, that is AB dagger and AF dagger. Now we can use this trick for global symmetry. Now consider a Lagrangian where multiple fields are there. Okay, so I runs from 1 to n, and it has a symmetry of SO to n because it's a complex field. Okay. Now corresponding interacting theory preserving supersymmetry is this, and for free theory the corresponding W is xi square. Okay, that gives you this free theory. Now, why I have said it is just a detour from the thing we are trying to do. Usually, this procedure is used extensively in calculating index for any interacting theory. Since index is invariant under coupling constant, and if you change potential smoothly, it doesn't change. You can change this Lagrangian to this free theory, and in this free theory you can calculate the index. But we are not going there. It is extensively used there. So using our new trick, the free theory, so we will calculate the partition function using this new trick. Okay, we will not calculate the index. but it was used. So previously we had one bosonic creation operator, but here we have 2n number of bosonic creation operator with an index I, okay, and 2n number of fermionic creation operators, okay. Now this means that ZBX is equal to ZBX is equal to 2nx, and it is, as I said, the single letter partition function just add up, okay. So it's a 2n number of x and 2n number of x here. Now you can calculate easily that P of platistic exponentiation of 2nx, okay, is exponential of 2n times x to the power n. So here you see that it is not an exponentiation of the full thing, because it was ZB to the power ZB function of x to the power n, not ZBx to the power n. So that's why this became 2n x to the power n. So 2n comes out of the sum and it gives you 1 by 1 minus x to the power 2n. Okay. Now you can calculate the fermionic platistic exponentiation in the similar way, and it gives you 1 plus x to the power 2n. Okay, and you can multiply these two answers to get the full partition function, that is 1 plus x by 1 minus x to the power 2n. Now this matches with the expected answer and answer people have already calculated for this theory. Now sometimes it is convenient to keep track of the chemical potentials. Here we are talking about SO2n symmetry, right? Now SO2n symmetry doesn't have only Hamiltonian, it also has Cartan generators. So it is important to keep track of all the Cartan generator charges, and you can define a new partition function which is defined by not only trace of x to the power h but by a multiplication of ai to the power j. Okay, gi are the Cartans of the SO2n. Okay, good. So now we know that boson so boson transforms in fundamental representation of SON like a vector, and that's why since it transforms in the fundamental representation of SON, the working principle of the prescription is how to calculate the single letter partition function is so this is the single letter partition function. You have a single letter AB dagger, and it is multiplied by the chi fundamental. Okay, so the character for this fundamental representation of SO2n. Okay. Now as I said that this is the character of the fundamental representation. Now if you put a is equal to 1 here, ai is equal to all ai is equal to 1, then it becomes the previous z for the same thing. Now here you can put ai is equal to 1, it gives you 2nx. So it's one very small check that it actually matches with the thing. Now you can calculate the ZB to the power x. Okay, now it becomes exponential. So now we have the single letter partition function. We want to calculate the platistic exponential of this ZB to the power xa x comma ai, and that will give us the bosonic partition function. So what is the formula? We have said that so let's check what is the formula. Exponential of 1 by n fx to the power n, right? So it is sum over n, 1 by n is equal to 1 to infinity, ZB of x to the power n, ai to the power n. Okay. Now it becomes exponential of sum over n is equal to 1 to infinity, 1 by n x to the power n. Now a1 to the power n plus 1 by a1 to the power n plus dot plus, sorry, this n is capital N plus 1 by n to the power n. Okay. Now individually you can do the sum, and it becomes exponential of minus log of 1 minus x a1 minus log of 1 minus x by a1. You can easily see that individually this x to the power n times individual terms has this log form, and that's how you can do the whole sum with log of the same thing with an. Okay.
Sorry, Suman.
Yes.
Are you working with SO2n? I'm a bit confused. You have n cartons.
Yes.
So it should be SO2n or something, right?
Yes, that is true. 2n number of bosonic and fermionic Clausius operators.
No. I'm talking about the chemical potentials. So it should be fundamentally represented SO2n, you mean, in the top of the slide. No, in this slide.
Oh, yes. Yes. This is the SO2n cartons, and that's where the this character of this fundamental representation.
Okay. So this is a vector basically.
Exactly. And that's why it's a vector, and that's why it's a fundamental representation, and that's why the character of that actual representation comes. So you can easily see that this individual sum becomes a log of this form, that log of x times a1, and the second one is x times x by a1, and that's how x times an and x times an and x by an. Now all those terms got multiplied, and this gives you this product. So this answer comes. Okay. So 1 by, because there are minus sign, and there is a product because this kind of product 1 minus x a1 times 1 minus x by a1. So this is the bosonic partition function. Okay, for with the Cartan charges. Okay. Now similarly, you can calculate the ZF. ZF is exactly same. It doesn't depend on whether it is fermion or, because it's in the fundamental representation. Now you can calculate the P tilde, that is the fermionic plethystic exponentiation of this ZF, and using the same thing but with a particular minus signs, you can actually show that this is not the division but the product of product above. Okay. Now you have the ZF and the ZB, and that gives you the total partition function, that is this. Okay. So this actually matches with the known answer. One quick check for this is, if you take again ai is equal to 1, you can see that it becomes 1 plus x to the power 2n by 1 minus x to the power 2n here, right? So here you can see that this is happening, and this gives you 1 plus x by 1 minus x to the power 2n. We actually derived it. Okay. Now, what is the advantage of keeping track of these Cartan charges? Okay. So the advantage is this, that we can compute partition function over states with a given representation of the global symmetry. So basically we are not interested in the full partition function, but to a particular representation we want to project our partition function, and that we will use in our calculation. And that's why keeping track of these Cartans are very important, and we can project it by this. There is a okay, why the chi, the fundamental representation character is sum over ai times 1 by ai. Okay, I just took the answer for the character, but right now I can't say how the character is calculated. It's a very basic thing, but
can I say, if you allow me, I can say.
Yes, please. I don't remember how to calculate this character.
So basically, you have SO2n, and SO2n means you are in R, its rotations in R2n, and the Cartans on SO2n are just pairwise rotations. There is rotation in 1-2 plane, 3-4 plane, 5-6 plane, and so on and so forth. So n such planes, all the rotations commute with each other, so they form the Cartans. Okay. Now you take a vector and you ask, how do you kind of look at these vectors and how do they transform under these rotations? Okay.
I see.
So a vector has, like, basically two components in each of these planes. Okay.
Yeah.
Let's say you have take one of these planes. Let's call it x and y. You can consider x plus iy and x minus iy. One of them will rotate by e to the power I theta under this rotation. Another will rotate like e to the power minus I theta under that rotation. Okay. Yeah. So hence, there are 2n components. Okay, and the 2n components, the charges under these rotations are given by, like, the first component has a +1 in plus under first Cartan, second component has plus minus under the first kartan, third component has plus only under the second kartan, fourth one has, and so on. So forth. Okay, and then you just write down the partition function and you get this. Does it answer your question?
Yes, yes. Thanks. Thank you very much. Great. So yeah. So yeah. This is actually okay. Thank you. Okay. So why we should keep track of these kartans is, and we have said that we want to project it to some representation, and the projection formula is used by this orthogonality relation. This is a orthogonality relation between two irreducible representations, and using this Haar measure, if you integrate, you can see that they will click if these two irreducible representations match. Okay, so where n is the rank and cardinality, and these are details, but this orthogonality relation can be used in this calculation. So so how to project that? If you want to calculate a projected partition function to a particular representation R, you can multiply by this total, this identity. You can put the identity inside, and then you can so it is like a basis function of this R representation, and this is the full answer, and this is the measure, and that gives this measure times this particular basis function projects this Z to this particular function. So this is the basic idea for this formula. Okay, now this is being used in this calculation to project it to something particular representation, and it's actually we'll use the most easiest representation, that is the singlet. Okay, we will project it to singlets to construct our Lagrangians. Okay, good. So particularly, so as I said, that particularly we will project it to singlets, and for singlets the character is 1, so that becomes this is 1. So you just have to integrate over these j's, and this is like a zero mode of this full partition function. Okay, and this is the answer we are seeking for. Now a very good reference for this part, whatever I said about the plethistic exponences and its use in superconformal field theory, there is a recent review or lecture notes by Abhijit Gadde, and this is the archive number. Okay, now we will implement this trick in our calculation. I said I will concentrate on the classification of the Lagrangians. Okay, we want to classify all possible Lagrangians coming from scalars and photons and gravitons. Now first, to start with scalars, our goal is to count the number of independent local Lagrangians which are quartic in phi. We are interested in phi, 4 particle 2 to 2 scattering. That's why it should have 4 phi's. It should be graded with number of derivatives, and we should calculate up to equation of motion. So you have to subtract out the equation of motion part. Okay. Now in any Lagrangian, in any 4 phi Lagrangian, what are the basic structures you will use? So that those structures are this: you have a phi and then sprinkle with L derivatives, and this is how you can construct a basic element of this so these are the space of such operators. Okay, now L can be anything from 0 to infinity, and we have to subject it to del mu del square phi is equal to 0. Now these derivatives are a vector, and it transforms under SOD symmetry, right? And we are considering only bosons, so we can directly use our previous result for the bosonic partition function, and we have seen that how the bosonic partition function can be calculated. Okay, so we will just directly use this relation, that is this is the 1 by product of these two things. We have just seen that this is the answer. Okay, now call this function as this D, particular double D. Okay, double line D. Now this answer is not exactly correct, and there are 2 reasons to it. One is previous calculation was done for SO2n symmetry. Okay, that is the argument is even number. Okay, now that means when D is even, we have the answer, and this matches actually. Okay, now for odd T the formula changes a bit. Okay, and the change is not very significant. significant, you just have to take a integer part of this and then multiply it to 1 minus x. So this is the answer, but it's not a very big change. But the next problem is, as I said, we have to subtract our del square phi operators because they are equation of motion and it can't be in the equation in the Lagrangian, because if it is there, it is just 0. Okay, so how to subtract that? Now, as we said multiple times, that for here, so the letters, the single letters are these derivatives. Okay, if you have a derivative, you just put x. Okay, this is the rule. Okay, now how to construct an operator including del square phi? What you will do, you will take del square phi and then act with again del mu 1, del mu 2, and then del mu 3, and that's how you will do it, right? So this is the basic structure which has one del square phi. Okay, now you can easily see that the answer will be exactly same with an extra del square, and that's why there is an extra x square. So you have the operators with del square phi has the partition function, that is x square times the same function coming from this sprinkling derivatives. Okay, now we have to subtract this part because we don't want the del square phi terms. Okay, now we want to subtract this part from the actual answer, and this becomes this, the d minus x square times d is the actual answer. Okay, so you have to multiply by this factor to subtract out the del square phi. Good. Till now we kept track of the terms of SOD because we have said that we need to project it to polynomials built out of the scalar letters to the space of SOD singlets. Okay, now this IS counts all possible structures with indexed objects also. Like you can have the structure has free indices. Okay, we have not contracted it yet. Now how to contract it? It is actually demanding that you want to project your partition function to the singlet. Okay, and singlet doesn't transform under SOD, and we know that scalars also doesn't transform under SOD. Okay, so that means we are constructing the scalars out of these indexed objects if we project it to singlet. Now you will so in that paper the authors have used this formula and used the actual IS here and then calculated the singlet. Okay, now the list you have seen in the talk. Okay, the list Shiraz has shown, it was the integrated version of this IS over this singlet. Now how to calculate the multi-letter partition function? Now till now we have done only single letter partition function, and now we will construct four phis and then derivatives. Okay, now how to calculate that? It is done very easily by this formula, that it's the same exponentiation up to a very small change, that is t to the power n. You just add a t to the power n to count the number of derivatives you are taking, and then you just take a number of phis you are considering, and then you just Taylor expand this exponentiation and calculate this IS for a particular k letter partition function. So this ISK is the k letter partition function. Okay, and one can check very easily by expanding this, that if your k is 1, then it is just IS. We have this particular IS. Okay, good. Now we are interested in the 4-letter partition function because we are considering a 2-to-2 scattering. That is, there should be 4 field components. Okay, now you can expand that Taylor expansion in Mathematica and you can easily check that this is actually true. I have checked it. Okay, this includes operators which are total derivative and they should be excluded. Now we have constructed all possible indexed objects, and it also includes total derivative terms. Okay, total derivative term means this, that del mu 1, del mu 2 acting on the full thing, so it can be indexed. And then also if there is a outside derivative, then that is called a total derivative term. Okay, now you have to subtract those terms because that will be anyway out of the game, because that will be boundary term. Good. Now total derivative, we have to exclude the total derivative term. In the CFT language, this means we are only concentrating on the primaries of the primary scalar quartic operators. Okay. Now, if we say that the character for the conformal primaries is just px, okay. Now for primaries there is px, and then there is descendant. Descendants are nothing but having derivatives, multiple number of derivatives on top of that. Okay. Now, as we said that any number of derivatives acting on this this kind of things acting on anything, it the partition function can be calculated just by multiplying this dx. Okay, so you have the primary partition function, and then you are sprinkling derivatives like this, and then that means you are just multiplying by d. Okay, so this is the full partition function for all possible 4-5 interactions with index. Okay. Now that should be equal to the IS4, this 4-letter partition function, whatever we calculated, because this includes everything. Okay. Now this is this, but we are interested in this px only. Okay. So that px is just IS4 by this d. Okay. So this is counting the number of interactions with without the derivative, without the total derivative. Okay. Now we are in business that this gives the counts for all index structures up to this total derivative, and now we want to construct the scalars. Scalar Lagrangians, or we want to project it to singlets of the SOD. Okay. Now we have said that the projection to SOD means you just integrate over the Haar measure. Okay, and that gives you the singlet partition function, and the chi corresponding to this is 1, and that's why this formula is true. Now it only depends on x. Okay. And this was done explicitly. It is hard to do analytically, but numerically people have in Shiraz's paper they have calculated it, and they have seen they have generalized the answer for various dimensions, and this is the answer for scalars. Okay, you have seen this list in Shiraz talk. Okay, where d is this particular function. Now this counts parity even and parity odd functions, and parity odd means structures with epsilons. Okay, Levi-Civitels. Now one can write this single letter partition function for scalars like this. They can Taylor expand the partition function with derivatives, and this means that this is the spin 1 representation of SOD character. Okay, this chi 1 box means spin 1 representation of SOD character. Now this means spin 2 traceless symmetric representation of SOD character. Okay, so if you Taylor expand this, you will actually get this. You can calculate the these quantities, because you know what is this ISAI is. I just told you. And you can Taylor expand it, and you can check this is actually true. Okay, and chi-rs of the characters of this representation are of SOD. Now for photons, I just showed you this expansion because this will be very useful in the next slides. Good. So scalars are done. These numbers actually matches with the number of S matrices Shiraz has shown in the previous day. Okay, this exactly matches. Okay. Now for the photons. What are the basic structures? Yeah.
Maybe we can pass and ask whether there are any questions.
Yes. If there is any.
Maybe.
No. Okay. Good. Okay. So for photons, how to construct a photon S matrix. Okay, now you want a gauge invariant S matrix, and that's why the thing starts with F menu, and you have to act derivatives on this F menu. So this is one structure, F menu acting on derivatives multiple times, and this is one structure. Now you take 4 such structures and then contract as many ways as you can do. Okay, this is how you can construct a Lagrangian for photons, right? So now, the same thing that previously we had del acting on phi's. Now we have del and multiple dels acting on F. This is the basic structure, and this is what I just wrote. subject to this condition that this is an equation of motion. If somehow taking all those derivatives, while taking these derivatives, if you encounter this structure, then it should be 0. It can't be counted. Okay. Now, if you get this structure, that is Bianchi identity, you can easily check that this is 0. I mean, this is identically 0. Okay. And also you can check this is 0 because photon has null momenta, and also it is true that you can show that Bianchi identity and the equation of motion implies this condition. Okay. And also, since photon has null momenta, any derivative acting on this field will give you k square, and that k square is 0. Okay. Now, how to represent these things in Young tableau? Now, whenever I'm drawing an Young tableau, it represents an SOD symmetry. Okay. Now, H menu is an antisymmetric thing, and we know that columns represent antisymmetric. Now, here the derivative acting on H menu antisymmetrized totally. So this is like this. I just wrote this del to remember that one of the index is for this derivative. Okay. Now, if you calculate this, you can show that it is in the mixed representation if you impose these conditions that these two are 0. This is 0 and the equation of motion is 0. You can show that this is the only thing left. Okay. Good. So now we will start taking derivatives from this F menu, and we will do it Young tableau way. So this is the F menu. You are just multiplying a derivative. Now derivative can so this fusion rule is this. We all know that you can just put this derivative here, or you can put this derivative here, or you can contract these two derivatives. Okay. Now you can easily see that this and this are exactly same. So this quantity is not there. This structure is not there because of the Bianchi identity, and this means the contraction of one index from F menu with the derivative. So that exactly means the equation of motion. A derivative index is contracted with this F menu index. Okay. So this is the equation of motion, and that's why this is 0. So there is only one structure left if you take one derivative on this F menu. Okay. Now you take another derivative. So this is the only surviving structure in the previous step. You take another derivative. How the Young diagram works? You can take this derivative here. You can take this derivative here. You can take this derivative in down. You can contract these two derivatives and this. Okay. Here there is a tail. Okay. So you can contract these two derivatives. Sorry. Yes. And here also you can contract these two derivatives. This derivative and this derivative can contract. Okay. And now we will do one by one. Now here you can see that two dels are in antisymmetric combination. This can't be there because derivatives commute. Okay. We are doing flat space. So in flat space derivatives commute, and that's why this is 0. This is it. You can't antisymmetrize derivatives. Here this part is 0 because of the Bianchi identity. Okay. So, and here you can see that derivative is contracted with one of the indices of F menu, right? So that means it is equation of motion, that is 0. And here two derivatives are contracted, and that's why this is 0. So you can easily see that all the terms are 0, and only term surviving is this. Now you can do it multiple times. Okay, you can do n times. You will see that the only surviving term in every order is just this. Okay. Now there is a very simple reason for it. What you are doing, you have an F menu, and then you are putting a derivative. Now how to put the derivative? It is, I mean, you can't you can't put the derivatives here at any time, because that will be in antisymmetric combination with another derivative. So that means you can put on, so there can be only one derivative antisymmetric with the polarization. Others have to be symmetric since the derivative commutes. Okay, and that is the basic reason why this is the only basic structure. Okay. Now, since these are the basic structures, and we have seen there is a Taylor expansion series and there is a general formula for it. Okay, we have written down the IV. Now you can ask why this is starting from x square and x cube, not 1 and x. I have told you, if a structure has a derivative, you should put an x. Okay, so you can see at this structure, what is this? This is 2 box. What is this 2 box? 2 box is just F menu, right? So F menu has one derivative, right? So F menu has one derivative, and that's why you have given an x. Now in this structure, you have 2 derivatives. acting on, so this is f mu and times another derivative. So that's why there is x square, and that's how this is done. Okay, so this is basically counting the number of derivatives with this character. Good. Exactly, that's what I have written here, that the first term is f mu and it has one derivative. Now all of them has coefficient 1, since they are the only structures at each derivative order. Okay, now there is not many, every time we see that there is only one structure at every derivative order. Okay, so these are precisely the representation of the vector spherical harmonics also, like the scalar spherical harmonics. These are exactly the vector spherical harmonics basis. Okay, and this is the reason why this spherical harmonics are very important in this 2-to-2 scattering procedure. Okay, now till now what we knew. Okay, now we'll calculate this IV. Until now we know that this IS is this 1 plus x chi of this representation, and then this there is a Taylor expansion. We have seen IV has this Taylor expansion, right? So now, and also we know that IS explicit form, this D we explicitly know, we have calculated it. Okay, now let's calculate one thing, that is this IS times x times chi. Okay, just for fun, we can calculate this quantity. What is this quantity? This is this x times this, you have to put this IS expansion here. Okay, and now you have to multiply all of them. Okay, now chi, so now this becomes x times chi. First chi will multiply with 1, and then it becomes x chi 1 box, 2 box, and then 3 box, and then 4 box. Okay, so this is just, so this is like this box. Just one second, I should do this. Okay, so this box multiplying with this box becomes this. One of them is this, right? Another one is this, and another one is just this, right? Because you can contract them. So this is basically, this is what is happening here in these 3 lines. Okay, so here, so in the first line, these kind of multiplications are happening. You are just increasing by box. In the second line, you are contracting. So this is this kind of multiplications are happening in this second line, and in the third line, this antisymmetrized kind of contractions are happening. So this is the formula. As I said, that the first line is traceless symmetric product, and second line is the taking the trace, that is dotting with each other, contracting it, and the third line is antisymmetric product. Now you can see that this is the part having these vectors. Vector has this Taylor expansion. Okay, others we know from the IS, because these are the scalar quantities. And exactly this is what is written, that this multiplication IS times chi is this IS and then x square times IS. These are the 2 lines, and then this is the third line. Okay, IV. Now you can explicitly calculate this IV. IV is this quantity. Okay, what is the time? 2 to 3. Okay, 1 hour. Good. So IV is this quantity. Here you can see we know all the quantities. We know this D. We can calculate this chi delta by calculating a Taylor expansion of this IS. You know this IS. You know this IS form. You know how to do the. You just take Mathematica, do the Taylor expansion, and take the linear term. You will get this chi, right? So you know this also. So now you know IV. Okay, and the similar way you can calculate for the gravitons. Here one identity I have just used, that for 2 representation, this is actually true. If there are in direct product, then this is just chi R1 times chi R2. Okay, the direct product representation character is just multiplication of the individual characters. Okay, so this is what I have used here every time while doing this multiplication. Good. Now for gravitons, the same rule, the same game, that you want to calculate. So the basic structure is R mu nu alpha beta. Okay, this is the first structure you get with all the symmetries. Now R mu nu alpha beta has this decomposition in terms of these SOD things. This is the wild tensor. SOD, every time you have to make it traceless to make a SOD representation. So that actually represents the wild tensor. And the second term is Ricci tensor, and the third is Ricci scalar. Okay, this has no indices. Now Ricci scalar and Ricci tensor are zero on cell, because if you calculate if k square is 0, and if you calculate h mu a to the power ikx for and if you calculate this Ricci tensor in Ricci scalar, it becomes 0. Okay, so so now for gravitons, the constraints are this. This is the equation of motion, del mu r mu nu alpha beta, and this is the Bianchi identity we know. Okay, so these are the constraints, exactly like the photons. Shiraz said it was exactly same, just it works exactly like a product of two photonic cases, like two photons. Okay, so the similar procedure can give you this tensor single letter partition function like this, and similarly you can calculate this chi double del like this.
Sorry.
Yeah.
So you said Ricci scalar and Ricci tensor are 0 because of the equation of motion, because we don't have energy momentum tensor, or you said something else I missed, I guess.
So Ricci scale. Oh yes. I mean the equation of motion is just one second.
Yeah. So there is no energy momentum tensor. That's why these are 0. Okay.
Yes, exactly. These are free particles. These are interacting, but at starting they are free particles. Okay. Yeah. Exactly. So this is why R and R mu nu, both of them are 0. Good. So now you can also calculate here. You can the similar way IV you can calculate it. You just take another derivative. Okay, and then you can calculate it, and all these quantities except this term, and this also can be done by a Taylor expansion of this IV, because IV expansion, and the first term will give you this guy. Okay, good. So now we have the single letter partition function for scalars, photons, and gravitons with 4 components. Okay, this we have. Okay, next we have to calculate the so this is the single letter partition function, and next you have to calculate the 4 letter partition function. The 4 letter partition function formula is exactly easy, like you take the same formula with t to the power n, Taylor expand up to t to the power 4, and then take the coefficient, that's the 4 letter partition function, then divide by a factor to subtract the total derivative terms. Total derivative terms always comes with the same factor, that is this d, capital D. Okay, you just have to subtract the total derivative term, and then you get a structure up to total derivatives. You got an indexed objects, like all those things are indexed. Now you have to integrate over the Haar measure of the SOD and to project to the singlets to construct the scalar Lagrangians. Okay, so this is how you can construct the scalar Lagrangians for graviton, photon, and all those scalars. Good. So all these things are explained for the scalars, and it was shown in 3rd lecture also. Okay, but there is one subtlety in this counting procedure. Okay, what we missed actually in this naive counting procedure. Okay, good. So partition function for photons, if whatever I said, if you follow all these things, you can show, and also Shiraz showed in the lecture, the list that d greater than equal to 10, d is equal to 9 to 3. Okay, all those things are shown. Now you can so every time you will see this multiplication by this d. Okay, because of that division factor, that is every time you have to take only total derivative, you have to subtract out the total derivative. Now that's why this d factor is coming, and d is, to remind you, d is this. Okay, we'll let us see what is the motivation behind this, why this d comes. But you will see in that list, if you see carefully, that you will see this kind of minus signs, that minus x to the power 5. It's stray minus x to the power 5. Okay, so these are a bit different, and that comes from a particular mistake in the counting. So in the plaffistics counting we have followed has 3 steps, 3 main steps. Okay, the step 1 is computed the partition function built out of 4 letters. Okay, this is the first step, as we said. The second step is subtract the total derivative by division of d of step 1. Okay, Now the third is integrate step 2 over the SODE to isolate the SOD singlets. Okay, so this is the basic steps I explained multiple times. Okay, but there is one assumption in this all these things, that we have identified this whole procedure with the counting of those primaries and then descendants and all those things, but we forgot one thing, that we have assumed that there is no null state in the module. Okay, now if you have a null state, and that is exactly what is happening in this d is equal to 9. Okay, now at d is equal to 9, step 2 has a mistake in assuming that there is no null state. Okay, but this is wrong. In d is equal to 9, you can write these j mu, particular j. Okay, you know the notation, that is you just take the wedge product of these 4 f's, and then you take the dual. So that is, you just multiply by an epsilon, big epsilon, 9 index epsilon, right? So it's an identically conserved current. If you calculate the del mu on j mu, this j mu, you will see that it has a so this is actually identically 0. It's an identity on f. Okay, so given the definition of f, it is 0. Okay, now how many derivatives are there in this? So if you have overcounted this, okay, and how many now we have to count how many derivatives are there in this del mu j. You can easily say that there is one derivative in this f. So 4f has 4 derivatives, and there is another derivative outside, that is del mu. So this is a scalar, like del mu j mu is a scalar. We counted it wrongly, we have to subtract it. So that means we have to subtract an x to the power 5 from this answer. Okay, and this is so easy, and this is how there are some correction terms in the list. You see that there are some subtractions, and subtractions are exactly due to this kind of charges, which are exactly 0. Okay, so this gives a way. This gives a way to count and list all possible 4-point interactions graded with derivatives. Okay, so this is how. So these are the partition functions. What you have to do, you have to just Taylor expand in x, and then look at, let's say, x to the power 10 or x to the power 20. Okay, and then we will get a coefficient for this, right? So any quantity like this can be Taylor expanded in x, and then you can just calculate that x to the power 10 coefficient. That will be just a number. Okay, and that will be an integer. That is also a very important thing, that you have to get an integer, otherwise it represents the number of things, number of Lagrangians, valid Lagrangians, right? So that happens, and that exactly matches with the number of S matrix you have calculated at the same derivative order. Okay, good. Now we will roughly so similarly one can count the number of S matrix structures constructed from the Mandelstam variables. Just using the Mandelstam variable, you can construct your structures as yes.
Yeah, sorry, just one question.
Yes.
Regarding the previous slide.
Yes.
So this again has to do with the question that I asked in the beginning.
Yes.
You're not including A wedge, F wedge, F wedge, F.
Yes.
Is that correct? That you know, like or something like that in 8D? Do you have such a term in 8D? Like,
do you have such a term in
sorry, 9D
9D?
9.
No, I don't think there is any structure with a stray and bare A. So
but you do have such terms, right?
You do have. Yes.
So what is the statement? And that they don't lead to S matrices. They also contribute to S matrix, I think. Right?
Good. Yes.
Confused about this, but okay.
I have no answer to this. Okay. Yeah, I'll let you know. Yeah, I right now I don't know why those terms are excluded, or whether it is in. No, everything's are constructed out of only F's, so it can't be that. Yeah, I don't know what to say.
Okay.
Good. Okay. Okay. So here, they have shown the one-to-one correspondence between these two lists. No, I should ask one question. What kind of S matrix it gives in the Mandelstam variable things like?
I don't know, but I would think it would give you a scattering. It will give you vertex, but
It will give you a vertex. Yes,
okay.
I can think of a 3-point vertex, but so just for once, can I write one Lagrangian kind of thing?
Let's say A wedge F cube, A wedge F wedge F wedge F, 3Fs.
I see.
So this
Yes.
is the 7 form.
Yes.
Right?
Yes.
Add in D equal to 7. And it's not a total derivative.
Yes.
And it's not made out of Fs.
Exactly.
So it's not gauge invariant, but if you do a gauge transformation, it will give a total derivative.
It will give a total derivative.
So it's allowed, but it's not gauge
I
invariant.
see. I see. I see. I'll think about it. I have not checked myself. So I mean, yeah, it's a paper where I was not there, and I was a bit skeptical about this big paper. But yeah, I mean, I have not done this calculation myself. I will check this and then I'll. Yeah, this is a good thing. I should know this. I mean, I'm sure they know it. I just don't know. And yeah. Hello.
Yeah.
I just don't know. I mean, they definitely know it. Yeah.
Let's contribute to the equation of motion, as you can check. I mean, so it should contribute to the S matrix.
Yeah. It should contribute. Yeah. Okay. No, I'm just thinking why this is not coming in this S matrix counting. Okay, fine. I will read about this. Yeah. Sorry. Yeah. Okay. So so here we will roughly state how the S matrix are constructed. Shiraz has said this in detail. Okay. Now for the scalars, what we just want, we want a function only of momenta, and that means two Mandelstam variable S and T, and the U is related by this relation. Okay. Now parity odd S matrices are given by this kind of structures times and f of S and T. So this is how one can construct various kinds of S matrices out of momentas, and in particular dimensions this kind of structures can be there. For example, this is in T is equal to 3. Okay. So you also have seen, and these are a few discrete statements, like you have seen this in the previous lecture, but I just wanted to say it once again, that you have seen the relation that S4 mod Z2 cross Z2 is S3, and Z2 cross Z2 keeps STU invariant. Okay, Z2 cross Z2 is kind of a transformation, transform both of them at the same time, like 1 2 and 3 4. 2 and 2 3 and 1 4. This kind of elements are Z2 cross Z2. Okay. So since Z2 cross Z2 keeps STU invariant, S3 is the only non-trivial part in this STU thing. And action of this so now we have to construct polynomials of S and T. Action of this S3 on this polynomial of S and T is best realized by the permutation of STU subjected to this condition. So we have to consider that this condition is there, that STU S plus T plus U is 0, and you have to construct polynomials with some particular symmetry of S3 permutation group up to this condition. Good. You have seen the list in the previous lecture that the 0 degree polynomial is just 1 degree polynomial is there are 3 options, but these are effectively S and T up to this S plus T plus U. So second degree polynomials, there is symmetric, there is mixed symmetric, and there is no antisymmetric. At the third order, the antisymmetric starts. Okay. Now here I have said you that the derivatives are getting counted by x. Okay, so every derivative corresponds to x. So here in this counting, every momentum will correspond to x. Okay, so momentums are like letters. Okay, So it is very useful to count all the polynomials by their representation into a partition function, and the partition function is the same. Okay, 1 by 1 minus x square. So these are expressions which they have derived in the paper. Okay, so you can calculate this. So 1s and 1a z tilde representation. So partition function for this 1s and 1a. Okay, by this formula, and this exactly comes from the t to the power 3 term in the three letter partition function. Okay. So these are formulas given in the paper, where this zeta tilde, the partition function for this R representation is this, where NRM is the number of S3 representation of type R of degree M. Now I will give a good motivation for these formulas later. Okay, so these are very formal expressions which you can calculate. Given this Zx, you can calculate this Z tilde 1s 1a, and you can see that the same functions are coming. That is the same D is coming. Okay. So here also till now these tildes are without the condition that is s plus t plus u is 0. So all tilde components doesn't include s plus t plus u is equal to 0. Now we have to subtract all those s plus t plus u is equal to 0 kind of conditions. Now what are the polynomials which has this s plus t plus u? So this has exactly like this, right? So this is like the same kind of, all possible polynomials times this s plus t plus u. So what should be the partition function for this? This is exactly the FST gives you this z tilde, the tilde without the s plus t plus u, and s plus t plus u gives x square. Why? Because they are just momentum square. S is just momentum square. T is also momentum square. So that's why that counted as x square. And we have to subtract this part because we don't want that structure to come. Okay, now that gives you the total partition function as 1 minus x square times z tilde r. Okay, so zr denotes the partition function over the polynomials in the representation r with the constraint this. Okay, so one can calculate this zr explicitly for 1s 1a, and I have calculated it, and this matches with the answer, and these are the answers. Okay, now there is a good different way to calculate the same thing, and D is this. Okay, now I will give you intuition why this kind of things are true. Now this is a check why this is happening. I have told you that this formula is z1s tilde is this. You just put zx is equal to this, and you can show very easily that this is what is coming, z1s. Okay, and z1 is this D. Okay, this is exactly D. Okay, now we will see how we can motivate this same thing in the 1s representation. Now what is 1s? 1s is the completely symmetric representation. Okay, now so what are this? So we have to construct completely symmetric polynomials. Okay, now there are two structures corresponding to this, that we know that any S matrix is just a combination of these two things. Other asymmetric combinations can be written in terms of this. Okay, so this is s square plus t square plus u square to the power m and s2 to the power n. So these are the complete structure. Like take any m and n, and this can be represented like this. Now this is one single letter, another single letter, and the single letter is the partition function is z1 is x to the power 4. Why x to the power 4? You have s square, so that means momentum to the power 4, right? And that gives you x to the power 4. Okay, so here you have the second single letter partition function, and that is STU. STU is the total dimension. So what is the total dimension of STU? Is p to the power 6, and there are 6 momentums total. Okay, and this gives you x to the power 6. So single letter partition function for this letter is x to the power 4, this letter is x to the power 6. We have said that you take the plastic exponentiation of this x to the power 4, and this gives you 1 by 1 minus x to the power 4. And this gives you 1 by 1 minus x to the power 6 for this second thing, and the total partition function is just 1 by 1 minus x to the power 4 times x to the power 6. So this exactly matches with this 1SZ. Okay, the previously you have calculated, they have in the paper they have calculated extensively. They have also shown that this is how one can. Okay, so this is how one can calculate. Okay, 1A is what? 1A is the antisymmetric representation of the SOD. Okay, now there I said you that in 3D in degree 3 this antisymmetric representation first comes. Okay, and that's where this and this is the only structure with the antisymmetric representation. So how to construct polynomials out of this antisymmetric representation? That is this: you take this antisymmetric structure and then multiply with a symmetric a to the power m and to the power n, and this is the complete antisymmetric structure. Now how to calculate this for partition function for this? You can see that there are 3 quantities and there is only one structure, and that's why there is only one x to the power 6. If there are m and p and random, any number can come, so then it would have been 1 by 1 minus x to the power 6, but this is just x to the power 6 because there is only one structure. Now here there can be multiple structures, and that's why this is 1 by 1 minus x to the power 4 is coming, and this is 1 by 1 minus x to the power 6 coming from this. Okay, so you have to multiply all of them, and this gives you x to the power 6 times d. Okay, so this is Z1a. This exactly you saw, Z1a is x to the power 6 times d. Okay, so this is how one can motivate all these structures. You can do the mixed symmetric also. Mixed symmetric has 2 structures, and that's why 2 kind of things comes with the 2 different derivatives. Good. So now we will go to, this is one of the motivations I wanted to tell you, and yeah. Good. So now we'll show something. We'll show a relation of photon polarization up to Z2 cross Z2 symmetry. Okay. Now this is a slight change of topic. So you have seen a decomposition of photon. So I mean, I should ask that if there is any question in this stage. Okay.
Yeah, I don't see.
Yeah.
Any.
Okay. So now you have seen in Shiraz's talk that a polarization for photon or any graviton can be it should be decomposed into 2 parts. One is epsilon parallel, one is epsilon perpendicular. The parallel is parallel to the scattering plane, and perpendicular is perpendicular to the scattering plane. Okay, this is how you can decompose it. And the plane is a 3-dimensional plane. The scattering plane is a 3-dimensional plane, and that's why the perpendicular part is SOD minus, has a stabilizer group SOD minus 3. Okay, and you can construct vectors, scalars, or tensors in this SOD minus 3. Okay. Good. Now a polarization for photon takes values from the space of scalars and vectors under SOD minus 3, right? So scalars means the polarization vector is on the plane, and vector means the polarization vector is perpendicular to the plane. Okay, and this construct the the Hilbert space. Good. Now for scattering space, so now we are scattering 4 photons, right? So now we are scattering 4 photons, and the space is what? The space is the same row. This is the row, the full space S plus B, and then direct product 4 times because they are totally independent. Okay. Now you have to project it to Z2 cross Z2, because we know there is a invariance under Z2 cross Z2. Okay. Now there is a well-known formula in CFT calculation that this particular quantity rho multiple rho to the power 4 projected to Z2 cross Z2 is just rho to the power 4 subtracted of 3 times symmetric rho and antisymmetric rho. So this S square rho and lambda square rho are like this, that you take 2 particle state and then symmetrize them, and another 2 particle state you antisymmetrize them, and the symmetric part is represented by S square rho, and the antisymmetric part is S square lambda square rho. So this also has 4 particles. These are 2 particles, this is 2 particles. So basically all of them has 4 particles, and this relation is true. Okay, this was shown very complicated way previously, but in this big paper, Shiraz and collaborators have shown a different proof in the partition function level. Okay, so now how to show this? You can call it a physics proof, and as they said it. Okay, so now you can consider a single particle partition function. trace over rho is the all possible Hilbert space. You have to sum over all those, and then the Cartham's charges to the power of the Cartham's. So what is this? So we are calculating a single particle partition function. That means one particle state, you take it and then sum over all i's. Okay. Now this as a definition, this is just the single letter partition function, that is z of ai. Okay. We have already calculated it. Good. Now we will calculate it to two identical particle partition function. Okay. As I said, for two identical particles, one can decompose this. Basically, this is rho square. So you can decompose this rho square into two parts. One is symmetric rho, one is antisymmetric rho. Okay. Now symmetric rho trace over the same thing is I1, I2, and then a to the power the same operator. Okay. This is the a to the power j operators. And then you project it to the symmetric part, that is identity plus 1 to flipping. Okay. So one can show that, one, if you have one, it just gives you the I1 times this operator I1, and then I2 times this operator and I2. So this gives you just square of the single letter partition function. These are totally decoupled. But in the P12 case, this P12 term is a bit different. And we'll see what is happening here. Okay, here 1, 2, I1, I2, and then operator, and then P12, I1, I2. So P12 acting on this I1, I2 becomes I2, I1. Okay, now I1 is getting contracted with I2, and that can only happen when I1 is equal to I2, right? And here we have to sum over I1 and I2. So here is a sum over I1, I2, right? So that gives you just. So the Cartan charges add up, and then it becomes a single letter partition function with a square, not z a whole square, but z of a square. This is a single particle partition function it became. So this is z of a square. So it becomes that z square a plus z of a square by 2. So this is exactly, this is written here. Okay, z square plus z of a square by 2. Now for the antisymmetric case, it is 1 minus P12. So this is z square minus z of a square by 2. So these are the two particle states. Okay. Now we will consider the full thing, that is the full four particle photon is or graviton or so graviton partition function. Good. So for total rho to the power 4 for full thing, this is the four particle state, and we are calculating a trace over this Hilbert space. So this is the sum over i's, and you can easily see that if you have an identity here, it gives you the same single letter partition function to the power 4 because they are totally independent. Okay. Now we want to project it to Z2 cross Z2. What is the projector to Z2 cross Z2? There are four elements to Z2 cross Z2. These are the four elements. Identity, this 2, 1, 4, 3, and 3, 4, 1, 2, and 4, 3, 2, 1. Okay. Okay, good. So you just put this projector here and then calculate it. So there are four terms. Four terms are like this. Here I1, I2, I3, I4 are totally intact. Here I1, I2 becomes I2, I1, and I4 I3. And here I3, I4, I1, I2, and I4, I3, I2, I1. This is how they are changing. And a to the power j is just a shorthand notation for this whole product. I just wrote it multiple times. Okay. Now first term, as we said here, that it is just z to the power 4. That is the single letter partition function to the power 4. Second term is very interesting. I1 is getting contracted with I2. And again, you can see I2 is contracted with I1. So there is only one delta function coming out of I1 and I2. And here also similarly, I3 and I4, there is only one delta function because I3 is getting contracted with I4, right? So that's why this delta I1, I2, delta I3, I4 is coming. And then a two particle, two state, I1, I3, I square, and then I1, I3. Okay, good. So here two index are gone like due to this Kronecker delta, and there is a two particles. This sum is left over. So basically this sum is left over with identity, whatever identity you have. Okay, and that gives you the z square of a square. Okay, the third term is this. Again, the third term is I1 is getting contracted with I3, and I3 is getting contracted with I1. So there is only one delta function. It is actually true. For Z2 cross Z2, this kind of things are coming up, that only two delta functions are coming. Okay. And this gives you again a Z square to the power A square. So this way, all these three terms are just Z square function of A square. Okay. So the full answer is just Z to the power 4, that is coming from here, Z to the power 4, and all of these three are 3 Z square of A square. I just wrote by 2. Okay. Four. Yeah. So now one can check that this term can be written like this: Z to the power 4, Z to the power 4 minus 3 times these two products. Okay, these two products are exactly like trace of S square row and trace of lambda square row. So and this is exactly trace of rho to the power 4. We have seen this. This is rho to the power 4. The full answer. This is trace of the same and the calculation we are doing, and here is the S square and lambda square. Okay, and you can show that. So basically, we have shown that the trace of the partition function over this rho to the power 4 modded Z2 cross Z2 is just trace of rho to the power 4 minus 3 times this S square row and lambda square row. Okay, and that gives you this. Okay, so this is a good proof up to in the partition function level, so that that this is actually true. Okay. Now I will come to the time ordering in chaos bound. This is 327. Okay, I'm almost done. Okay.
Maybe no we can pass and ask.
Sorry?
I was wondering whether to ask whether there are any questions and so on.
Yes.
Okay, so
yeah, this is a bit mathematical also. Yeah.
Okay.
I think I can go.
Yeah. Okay.
Okay. So now I will come to the final thing, that is the time ordering in chaos bound. How OTOC becomes a time ordered correlator in this CRG. So what is this bound on chaos says? That out of time ordered thermal 4-point function in large N theory cannot grow faster with time than e to the power twice pi by beta. This is the X bound, actual bound, chaos bound, and where beta is the inverse temperature of the ensemble. Okay. Now in appendix A of the same paper, the authors have explained that in special case of conformal large N field theories, they are bound also constrain the growth of the ordinary time ordered correlator. Okay, in Rege limit on the causally Rege sheet. Okay. So what is the actual reason behind that? I'll explain. Okay. So what they are doing, or what the actual logic is, that you take a large N CFT in Euclidean space and then angular quantize it. They have worked in angular quantization. Okay. So the angular coordinate is theta is Euclidean time, and radial coordinate r is the space. Okay. Now theta is periodic with periodicity 2 pi, as it is the angular coordinate, and the theory with in this quantization is effectively thermal with beta is equal to 2 pi. So and beta is the periodicity of the boundary time. Good. Now they are calculating a normalized correlator of this form. Okay, of this exactly particular form. O3, O2, O4, O1 is the ordering. Okay. Now we will see that how this ordering is working. So the coordinates for this in this Euclidean space is this. Okay, in their paper they have used O3 inserted at 1, O2 is at x is smaller value, and O4 is 1, O1 is again x is positive. Okay, here they have the theta coordinates are 0. Okay. Here you can see that I should write down the real value of theta. Real values are 0. This is epsilon. This is pi, and this is pi plus epsilon, if you can see, right? So this is exactly ordered in this real theta values, and this is the same ordering you can see here. So here the ordering is O3, O2, O4, O1. Here you can see O3, O2, O4, O1. So this is the ordering. Okay. So they are working in angular quantized way, and this is how the angular ordered. Okay. So this is ordered in real theta. Now this has a simple representation in the quantization of the same theory in usual Minkowskian time. You can analytically continue all those quantities, and what it actually does. Okay, what it actually does, you take these Euclidean coordinates. Okay, Euclidean coordinates as r cos theta and r sin theta, and if you analytically continue them, the time Lorentzian time, Minkowski time, becomes minus it, that is minus I r sin theta. This is the r sin theta is the Euclidean time, and this becomes minus r sin theta. Okay, now you can put the r and theta values from here to calculate the corresponding Lorentzian time. Okay, now one can easily see that the theta value for this is 0 and O3 is 0, or for theta value for O3 is 0 and O4 is pi. So that's where this Tm becomes 0. Okay, so this is the easiest part, that O3, O4, Tm is 0. Okay, now for O3, for O2 it becomes, if you calculate it, for O2 it becomes plus x sin h tau minus I epsilon. So how this is coming? So the formula was minus I r sin theta. So theta is I times tau minus I epsilon. So this I is making this sign to sin h. This is one thing. Another thing is I comes out of this sin h, and then it multiplies with this I and make it plus. Okay, plus x. So this is how you get this. For O2, the answer is plus x sin h tau minus I epsilon. Okay. Now you can Taylor expand it in epsilon. What it becomes, that it becomes plus minus x sin h tau minus plus I epsilon. This is very crucial now, and minus plus time I epsilon, and the minus is so plus minus the plus is for O2 and minus is for O1. Okay, so this is how these times are, but it doesn't matter which one has which one, but the only thing matters that the I epsilon has exactly opposite sign of this, and I told you that x and sin h tau both are positive. Okay, so this is where their parameterizations are. Now, if x sin h t is positive, then we know that time ordering means time is replaced by t minus I epsilon t, right? So basically, the I epsilon takes the opposite sign of this time. Okay, so if you have a negative time, you should use positive I epsilon. If you have a positive time, you should use negative I epsilon with relative quantities. Here, Tm is totally 0, so I epsilon is also 0. Here you can see that if you have a positive time, you have a negative I epsilon. And this exactly says that in this Minkowski time, these operators are in time order. Okay, so this is how these normalized correlators are calculated, and you can relate it to the KAWS bound, and CHC also comes. Yeah, so this is the end of it. And now you can ask if you have any question on the talks. Or here, like,
yeah. Okay. Are there any questions? By the way, Suman, I just looked up this paper, this long paper, and
yes.
and I think they just corrected by hand for these Chern-Simons terms.
Oh.
To account for it, they count the statistic counting, and then they add terms to account for Chern-Simons terms.
Perfect. Okay. Yeah. Okay. Yeah. I mean, as far as the counting goes, I can't remember. Yeah. I mean, actually, I just read the paper. I mean, I didn't work all those things. But yeah. Okay. Thank you. Yeah. That should be.
Yeah, but are there any other questions, comments, and so on? Maybe we should maybe we can wait. Okay, so
yeah, I mean, I haven't just naive question, I guess. I mean, all this analysis is done for four-point function, right? I mean, 2 to 2 scattering in a sense.
Yes.
I mean, what are the things that we can generalize it to higher points, and what are the things that are not generalized in an easier way to higher point functions?
Yes. So the classification can be generalized easily to higher point function, and this was the main motivation behind doing all this S3 in 1M. I mean, S3 is very simple, and I mean decomposing it into 1S, 2M, and then 1A, and all those partition function calculations. These were done, I think, to first of all to give a concrete definition what to do if we have S4 or other kinds of like bigger higher point functions. So this was kept in mind while doing this calculation. So exactly as you said, that the motivation was to go higher point function to do all this the formalism is there, but I think I mean as far as the classification goes, it can be done. But the point is, what should be the physical motivation behind it? I still don't know. Like, I mean, for higher point function, I mean, we can classify it, but we don't have a corresponding CRG or corresponding chaos bound in higher point function. So that's why it's other than that, yeah. Sorry if that was the question.
The gauge theory classification on the scalar classification, you know, like also it was not bounded in much by chaos bound, right? I mean, and or the CRG, isn't that right?
Sorry, gauge theory and
the scalar classification and the gauge theory classification. Like they also, there is no, I mean, CRG, does it say something, you know, like in that case?
For spinning.
Let's say just for scalar, like you did the scalar classification, right?
Yes.
Yeah. What I'm saying that's still a useful thing to do even without CRG. I mean, CRG is useful for, you know, like in this graviton and so on. But maybe I'm wrong. But like the scalar theory classification or the gluons classification, just classification of S matrices is still, I think, a useful thing.
Oh, definitely. Like for gluons and all, gluon calculations are done by Abhijit sir and Subham, and yeah. But 4-point function. I mean, I thought the question was about 5-point function or higher, right?
Yeah. So you can do 5-point and 6-point, right, for the gluons. Say.
Oh, I see. Oh, I see. You are saying there is a physics motivation behind doing a 5-point gluon classification.
And a 6-point gluon class.
I see. Okay. That is great. Okay, that I didn't know. Yeah. Okay. Yeah. Then definitely this is important. Yeah. Anyway, any kind of classification is good to do, just to have a concrete idea. Yeah.
Okay.
But the other thing, I mean, what could be, I mean, if one tries to generalize this CRJ conjecture to 5-point or higher point functions, we would need such criteria, right? All this classification and
Yes, definitely. Like, I mean, as far as this work is concerned, it was like this. You have a argument, you have a motivation behind the CRG conjecture kind of thing for 4-point function. Now you want to check it for all possible interactions. Now, how to do that? It's a better way is that do a huge classification and check term by term. So yes, if you have a CRG kind of thing, I mean, anyway, this classification is very good to do. But I mean, yeah. So if you have a CRG corresponding to 5-point function, then I mean, one have to do this classification anyway for higher point function to say something. Yeah.
Okay. Thanks. Thank you.
Yeah. I guess one thing is one can just do the calculation and see, one can try to guess what would be a strong enough bound. If you put, it will kill most things. So you can try to guess what the CRG conjecture should be. If you assume that it kills everything else other than say Einstein gravity. Like
I see. Yes.
okay.
You are saying so there can be 5-point contribution from the Einstein and other terms. Now you want to construct a rule which will exclude only the Einstein 5-point function but not others. Like sorry, exclude others, but it will keep Einstein 5-point function.
Yes. Yeah. So you can ask what will be the growth? What growth if you demand?
That can be a good conjecture. Yeah.
I mean, so that you would know what to conjecture, and then you might go back and try to prove some kind of bound when to prove it. You know, like So I think it's just a thing to do. I think it's just it's involved, but I think it's anyway useful. Even. But Anyway, any other questions, comments? Okay, if there are no further questions, then let's thank Suman, for his tutorials.